In these problems, we are evaluating definite integrals, but the functions in this case are a little bit weird. They are piecewise linear functions, so we have a lot of straight lines joined to each other at sharp corners. By now, you should have done some of this evaluating of definite integrals, and the basic concept is you have some curve, and from some set of values, over some set of values, you want to figure out what is the area under that curve. And there are many ways to do this. We estimate it with rectangles and Riemann sums, and then there are some other ways to get an exact value. Here, we're going to be able to get an exact value because these aren't really curves, they're collections of straight lines. So we can divide the areas we're looking for up into things like rectangles and triangles that we know how to get the exact areas of. So let's look at this first one. It says the definite integral from 3 to 6. So 3 to 6. So we're only looking at this area. And when I talk about the area under a curve, if it goes below the x-axis, we're actually looking at the area above that, and it gets a negative value. So we're going to count this area in here and put a negative sign in front of it. What I've got here, really, I've got a square that's 2 by 2, so that is an area of 4. And I've got this triangle that is the triangle of a 1 by 2 rectangle. The triangle is always going to be half of that rectangle, so this is an area of 1. So our definite integral here is going to be -5. If that how I found the area of a triangle didn't make sense to you, just use the formula 1/2 times the base times the height of the triangle. The base of this triangle would be 1, the height would be 2. That's going to come out to be 1, 1/2 times 1 times 2. Okay, pretty simple. There are a few little tricks that might trip you up, so let's go through a couple others. Here we want the definite integral from 0 to 6 of this function. So from 0 to 6. So we're going to have some part of the curve that's below the x-axis and some part that's above. This part will be negative, this part will be positive, and we'll add it together. So what have we got here? Well, we could split this into triangles. Now I've got a rectangle in the middle that's 2 by 3, so that's 6. Each of those triangles is 1. So 6 plus 2, so that part is 8. And then we've got actually -8. And then we've got a triangle that's got a base of 1 and a height of 2. That's going to be a positive 1. So -8 plus 1, -7. Okay, let's try another one. This one says uh, the definite integral from 7 to 7. What does that mean? Well, you start at 7, you don't go anywhere. Is there any area under the curve there? No. You'd have to move to the left or right to get some area there because there's no width to this interval. So that's got to be a 0. So that's one trick they might throw at you. Another trick is this one. Here, it's the integral from 9 to 7. So we're actually going backwards. That's going to change the sign of your answer. And the way you might think about it is to find the area under the curve, what you're going to do is take the area under the whole curve at 9 and subtract the area of 7. Uh, um, but in this case, we're doing it in the opposite direction. So what is this going to be? Well, let's figure out the area of this piece. I've got, let's call this a 2, 3 triangle here. So that is going to have an area of 3. 1/2, 2 times 3 is 3. And then we've got 2 more boxes there. So that is 5. So this is going to be a -5. So that's a little bit of work with evaluating definite integrals on these piecewise linear functions.